Yeah, good morning, everybody. Please, can you listen to me? Raise your hand. Why today's strength is very low? Any university exams going on? Today's strength is very low compared to last 6 days. Yes, last 5 days. Yes, some students gave me answer. I am very good. We'll do that. Okay. And Ashish told sir RAC I got, but RAD is confused. Let us do that. Chalo. Yeah, quick review. Everybody now, please join immediately. Yeah, first let us do quick review. Everybody, let us do quick review on what we studied yesterday. See, yesterday we continue doing register reduction technique. Okay, we continue doing register reduction technique. It is one of the basic requirements of circuit theory in lumped parameters. Now I gave a lattice network. Yes, I gave a lattice network, but this lattice network is not symmetrical nor balanced because this 1 is not equal to 4 and 2 is not equal to 3. So it is an unbalanced asymmetrical lattice. But here still I did ask resistance like RAB, input resistance, RCD, output resistance, okay, RAD, RBD like that. So if you look at RAB, here nothing is there. So here 3 is in parallel to 7, that is 2.1. RCD, if you look from right side, this is nothing there open. So 4 is in parallel to 6. 4 is in parallel to 6. Then RAD is 3 in parallel to 7. RAD 3 is in parallel to 7. RBD, if you see, this 4 is in parallel to 6. 4 is in parallel to 6. Okay, na? Then I extended further. Now this was the gate question, IES question. Yes, again do node shifting. After doing node shifting, we observe that these 2 ohms, 3 ohms, and 6 ohms are parallel. So first these 3 are parallel. 6 in parallel to 3, 2 in parallel to 1, 1 plus 5, 6 ohms. Right side, there is a dead short circuit across passive elements. There is a dead short circuit across passive elements. Answer is 0 ohms. And now here I need RAB by RCD. RAB by RCD. Now if you look from AB point of view, this becomes a balanced pitch because 3 into 1 equal to 3 into 1. This 1 you remove, then 6 is in parallel to 3 is in parallel to 2, that is 1 ohm. Okay, RAB is 1 ohm. Then when I go to RCD, again when you look from RCD, I wrote right side, the same network, I did node shifting by writing right side. And there you again observe that this part becomes balanced pitch and current will never flow through 3 ohms. So I remove that. Again 4 is in parallel to 4, 2 is in parallel to 1, 2 by 3. So now RAB by RCD is 1 by 2 by 3, 3 by 2 is the answer. Okay, na? 3 by 2 is the answer. Then this was another interesting. Yesterday some students were arguing. Yes, yesterday some students were arguing why can't this be a bridge? No, the reason because there is some other connection at this junction, and even for this there is some connection at this junction. We cannot argue directly as bridge. But the observation was, yes, but the observation was, yeah, the mesh currents will be equal but opposite in direction. So the branch currents in 2 ohm resistance and 4 ohm resistance will be 0. Now when current cannot flow through, okay, those elements don't contribute resistance, so I remove them. Then clearly 6 in parallel to 3, 2 in parallel to 2, 1, 1 plus 1, 2. So total resistance is 2. 16 by 2 is 8 amperes. Then this effective DC resistance. When it comes to effective DC resistance, I assume that I gave ideal DC steady state. Okay, ideal DC signal. For ideal DC signal, dV by dt is 0 and di by dt is 0, due to which inductor acts like short circuit in steady state and capacitor acts like open circuit in steady state. That is why I removed this part. Now the path resistance which is contributing is only 6 ohms. The path resistance which is contributing is only 6 ohms. Now here the switch S is closed, then intensity of lamp is dash. The switch S is closed, intensity of lamp is dash. Now what we observed is, once the switch was open, then also it is a balanced bridge. Then the total resistance seen by the source is resistance R plus resistance of the lamp. Even after closing the switch, yes, even after closing the switch, though this is not a branch now, and it is not a bridge now because this becomes a single node. Again here RR parallel R by 2, RR parallel R by 2, total R. Again the total resistance seen by the source is R plus R lamp. That means the effective resistance seen before closing the switch and after closing the switch is same. So current will be same. So intensity also remains the same. Then here I gave a balance bridge. See, this looked like a bridge-duty network. We call this as bridge-duty network, terminated by 6 ohms at the load. Okay, but this network is called bridge-duty. But though it is like this, sir, after doing node shifting, we observe it is a balance bridge where 3 into 4 12 is equal to 6 into 12. This 6 ohms won't work. Again, 5 is in parallel to 10. Okay, now then right side, if R total is 50, R is how much? So I simplified, sir. All 12s parallel 4. Then these three are series. 14 plus R in parallel to 60 plus 30 is again 50. So I got R. Now this is another IES objective, but the arrangements are quite different. Both are not bridges. Yes, first of all, this part and this part are both not bridges. Okay, because there is no cross arm or central arm. But in fact, this arrangement will give parallel combination of 4-4 and 6-6. But this is where a short circuit is in parallel to passive element. So there is a difference in arrangement. Both are not bridges, but the arrangement will make a difference. That this is not a short circuit, but this is a short circuit. So then I simplified by taking all these components which are working, and the answer is 28 ohms. Then we learned an important concept called dynamic resistance. Dynamic resistance is change in voltage by change in current. Static resistance is steady state resistance. Yes, static resistance is steady state resistance at an operating point. That is the difference. Okay, static resistance is steady state resistance at an operating point. So here in a linear component, and the ratio of V by I, static resistance, or dynamic resistance, delta V by delta I, both remain same. So in a linear component, static resistance is equal to dynamic resistance because they obey homogeneity or proportionality. But our component is non-linear. Now static resistance at a point I got, but dynamic resistance in this case due to change in voltage by change in current is definitely greater than the static resistance. Now that ratio I got, okay, by differentiating and substituting the given data, I observe that in this case, dynamic resistance is 2 times static resistance. Okay, that is a very interesting concept. Then characteristic resistance, it is that resistance with which if you terminate the network, the total resistance including the network also remains same. And you can construct characteristic resistance only to such networks which are symmetrical and balanced. Now we study characteristic resistance even in power system, sir. Yes, we study characteristic resistance in power system. For overhead lines, typically characteristic resistance or impedance is how much, are 400 ohms. And for cables, it is 40 ohms. Do you remember the standard bits? So that concept it is. It is that resistance with which if you terminate the network, the total reflected resistance including the network remains same. And it exists only for symmetrical and balanced. Now this is a balanced and symmetrical where ZA equal to ZD and ZB equal to ZC. Okay, that is the meaning there. Then I rearranged, but now simplifying this by converting into delta to star and equating RC and deriving, you will get the answer. But that is a very lengthy process. But shortcut is, yes, characteristic resistance is root ROC into RSC. See where we get this, actually this derivation comes in 2-port networks. Okay, characteristic resistance of symmetrical and balanced networks are root ROC into RSC. So that shortcut I applied. ROC means you open this. Okay, open this and see. Then R1 plus R2 is in parallel to R1 plus R2. But RSC, if you see, yes, these two in parallel. Okay, and these two in parallel and then series. That is 2 R1 R2 by R1 plus R2. Okay, and this characteristic resistance is root R1 R2. Then, yes, now this is an infinite ladder. Everyone should observe. Yes, it is an infinite ladder. Okay, it is an infinite ladder. Okay, and I want R. So, you know, mathematical infinity plus and minus 1 is infinity. So if this is R, you remove one segment, this also is R. Okay, so I lumped it, then I joined back, then I modeled this approximately, we get this answer. Okay, so infinity minus 1 is infinity, infinity plus 1 is infinity. So I removed one segment, I lumped it and I added back. Now I solved this. Yes, I got this answer. But how to justify these positive answers only? Yes, when all are linear, passive, bilateral. Yes, when all are linear, passive, bilateral elements, resistance has to be positive. So I took only positive. Now similarly, capacitor also same way I did and I solved. I got this answer. It has to be positive. Then I gave the gate bit. It is very interesting that this segment directly become RA. Cleverly you have to do, sir. So RB is 1 in parallel to RA. That is a shortcut. Then impedance also I did. Again here, there are two possible reactances. Positive reactance exists and negative reactance exists. See, in this problem, negative resistance is meaningless. But in this problem, yes, negative reactance is a meaning. But because the nature of the network is purely inductive, because all series arms are inductive and shunt arms also XL greater than XC, shunt arms also XL greater than XC, it is overall inductive. Hence, we should take plus 12 only. That is very interesting. Then the Q problem. Yes, we were in the Q problem then. Now in the first case, Q problem, I asked RAB. Okay, RAB is the resistance between opposite diagonals of the entire cube. You can make it planar and do star delta delta star, but that is a lengthy process. But I applied Ohm's law. What is Ohm's law? I gave voltage, I got current. That ratio is resistance. That ratio is resistance. Okay. Now, but to get that ratio, I took the advantage of symmetry here. Now read the symmetry definition again, everybody. Here all resistors are equal. Very good. But more than that, the real reason is the path resistance between AB in all the paths is amazingly equal. Okay, the path resistance between AB in all the paths is amazingly equal. Okay, that is the reason I could do confidently current division. Actually, they are not perfectly in parallel. It is a parallel natured network, but no two elements are directly parallel. See, it is a parallel natured network, but no two elements are directly parallel. But I still could do current division because of the symmetry, where the path resistance in all paths are amazingly equal. So in that regard, this I divided into I by 3, I by 3, I by 3, and I by 3 again into I by 6s, and here also I by 6s. Then all I by 6, I by 6, I by 3, yes, and overall I. Okay, now overall I. Then I confidently wrote a KVL. Yes, I confidently wrote a KVL. Okay, from that I got the answer. Okay, RAB is V by I, that is 5 by 6. Okay, and then once I got that, I extended further where all branch resistance R, then it is 5 by 6 R, or branch inductance L, 5 by 6 L, all branch capacitance. Yes. Now how I wrote capacitance, this is a KVL for capacitance. From that I got it is 6C by 5. Okay, na? It is 6C by 5. Conductance. Then reactance, impedance, same formula, susceptance and admittance. Then I extended to exclusive properties of symmetrical networks. Yes, if you can identify such nodes in any big network which are at same potential, I can join them and reduce faster. After applying this idea, now they are parallel. See, originally here in this cube, no two elements are parallel. But we did current division because of symmetry, where path resistance in all paths are equal. But here, that idea of joining nodes which are at same potential made these parallel. Then from 3 to 2, 3 1 ohms are parallel. From 2 to 1, 6 1 ohms are parallel. And 1 to 0, 3 1 ohms are parallel. And this is the answer. Then another important property of symmetrical networks is that they can be expressed as mirror image with respect to common axis drawn including the target elements. Okay. Another important property of symmetrical networks is that they can be expressed as mirror image with respect to common axis drawn including the target elements. Okay. That is the meaning. They can be expressed, okay, as mirror image with respect to common axis drawn including the target elements. Okay. Target elements. Okay, that is a thing that you have to understand. Okay, they can be expressed as mirror image with respect to common axis drawn including the target element. So symmetrical networks are mirror image networks. Okay, symmetry is a mirror image property. See, we also learned, suppose you remember when I was teaching unilateral bilateral elements. In bilateral elements, the VI characteristics are symmetrical mirror image in quadrants 1 and 3. Na? Yes, in passive bilateral elements, symmetrical characteristics of quadrant 1 and quadrant 3 means mirror image only. Na? So symmetry meaning is mirror image. That also is important. Symmetry is mirror image. Okay. So that also remember. So symmetrical networks are clearly mirror images. So from that also now I can say, suppose I'm moving from this A to B. Suppose I came up to here. Okay, because it is mirror image. See, from this point X, this point, okay, and this point and this point are at same distance, That is why they are at same potential. Suppose I came to point Y, and from point Y to this point, and this point are also same distance. That is why these three are at same potential, like 1, 1, 1. Here with respect to X, these three are at same distance, like 2, 2, 2. You remember? That is also another reason we can say the points which are at equal distance from the mirror image axis are equal potential. Reasons are very interesting. The points which are at equal distance from axis are at same potential. That is very interesting, na, sir. The points or the nodes. Okay, I say the nodes that are equal distance. Okay, from mirror image axis are at same potential, are at the same voltage. That is very interesting. That is why this 2 we joined and 1 we joined. But this is possible here when all registers are equal, etc. Okay, na? So that you remember. Okay, that is very, very interesting. Okay, na, everybody? Chalo. Now, based on that, I ask this question. Use the above two ideas given in note 1 and note 2. What are the note 1, note 2 ideas? First of all, join such nodes which are at same potential, and note 2 is mirror image concept. Now to find RAC and RAD. Chalo sir, very, very interesting. And I want everyone to listen here. First, let us do RAC. Everybody. Okay, everybody, let me do first RAC. Yeah, now I'm coming to day 6. Chalo. First, let us do RAC. Now listen carefully, sir. All these basics are important. Okay, I am writing again to explain, nothing wrong. Let us say this is A. Yes, and this is C. You see AC. Okay. Yes, AC, observe. AC. Okay. These are the opposite diagonal corners of a surface. You take any two, like these two, or between these two, are also it is RAC, or between these two also is RAC, between these two also is RAC, between these two also is RAC, like opposite diagonal corners of a surface. Not the entire cube. RAB is opposite diagonal corners of entire cube. Now, sir, let us first understand. See, all are 1 ohms, of course. Now, listen carefully. Here also, sir, see the conventional way is make it planar and do star delta. Okay, here also conventional way, if you are confused, make it planar and do star delta, but it will take at least 10 to 15, 20 minutes, it will take, sir, minimum. In aptitude, that is not the style. And moreover, if registers are not equal, that is another big challenge. If by mistake registers are not equal, please understand my question. If by mistake registers are not equal, everyone, yes, if by mistake registers are not equal, then the only way is to make it planar and do star delta. Listen, okay? So first of all, yes, here RAC are the opposite diagonal corners of a surface. That is the first thing. Second, if registers are not equal, and if you want to do even conventional, make it planar and do star delta, delta star transformation. Then you will get the answer. Okay, then you will get the answer. That is a real challenge. Okay, na? But here let us apply basics. First, I will try to apply Ohm's law. Now listen carefully, sir. Suppose if you try to apply Ohm's law by giving voltage, finding current, everyone listen, by giving voltage, finding current, is the path resistance between AC in all paths are equal? Listen carefully, sir. Is the path resistance between AC in all paths are equal? Here it is not equal. In RAB, yes, in RAB case, everybody please understand. In RAB case, that was true. In RAB case, the path resistance between AB and all paths are equal, so current divided into 3 equal branches in a further. But sir, yes, here the path resistance between AC and all paths are not equal because this is one of the shortest path. This is longest path. So you cannot do directly current division. First of all, current division we do if the elements are perfectly parallel. They are not parallel. Okay, first of all, we do current division if the elements are perfectly parallel. They are not parallel. Parallel nature, but they are not parallel. Moreover, the path resistance between AC and all paths are not equal. So we cannot directly do, yes, we cannot directly do current division. Okay, that is a big challenge here. We cannot do current division. Then what we will try to do? We will try to implement 2 important extra things. joining nodes which are at same potential and writing mirror image symmetry. So I should join such nodes which are at same potential. But directly looking between AC, we cannot identify that now. Yes, we cannot directly identify which nodes are at same potential. So what I will do first, I will write mirror image symmetry. See, the first step is, step one is, I will write mirror image symmetry. Mirror image symmetry. Listen carefully, sir. This is a shortcut. This is a trick here. The trick is how to write like this. The trick is how to write like this. Okay. See, now important property of symmetrical networks is they can be expressed as mirror image with respect to common axis drawn including the target terminals. See, what are the target terminals here? A and C. Now, see, A and C are my target terminals. Okay, now I will place it on the same common axis. Okay. Now remaining network I should write. So now in that regard, let us say this is node 1, this is node 2, this is node 3, this is node 4. Adjacent to this is node 5, adjacent to this is node 6. Okay. So now in that regard, if you see the same nodes I am placing here. This is like node 1, this is like node 2. Okay, opposite to 1, this is node 3. And opposite to this is node 4. Now adjacent to this is 5. Adjacent to this is 6. Okay. See, the placing, see, node numbering is not important. Don't by heart anything, sir. It is not about how you number. It is about how you place them. You can give X, Y, Z, W, anything. But how you are placing is important. See, when I am looking from AC, this 1 I wrote up, 2 I wrote bottom. Then opposite to 1, 3 I wrote up. Opposite to 2, 4 I wrote down. And 5 is splitted left, 6 is right. So like that, now mirror image will come. See, right side here. Now you join all these elements, you will get mirror image. Now listen here. Okay, first if you see, yes, A to 5, 1, A to 1, 1, A to 2, 1. Chalo, A to 5, 1. Okay, A to 1, 1. And A to 2 also is 1. Okay, 1. Very good. We got this. Then similarly, C to 1, C to 2, 1, C to 6, 1, C to 1, 1. Okay, C to 6, 1, C to 2, 1, and C to 1 also 1. That is also true. Then 4 to 5, 1, 4 to 2, 1, 4 to 6, 1. Okay, 4 to 5, 1, 4 to 6, 1, and 4 to 2 also 1. Then if you see here, 3 to 5, 1, 3 to 1, 1, 3 to 6, 1. 3 to 5, 1, 3 to 6, 1, and 3 to 1, 1. 3 to 1, 1. Okay, that is a big thing we did. Yes, that is a big thing we did. Okay, that is a big thing we did. Okay, now you see now. Now you see. Yes, after doing this, now you see now. Chalo, now you see. Now see, if I join, yes, if I join an axis, see if I draw an axis here. Yeah, symmetrical networks have an important property that they can be expressed as mirror image with respect to common axis drawn, including the target terminals. So this side and this side, if you observe, they are mirror images. Now you can identify which nodes are at same potential. See, with respect to this axis, the nodes which are at same distance are same potential. See, if I give some voltage between A and C, current will flow. But directly current division I cannot do now because no two elements are parallel. At the same time, path resistance in all paths are not equal. So division of currents is not possible. But because this side and this side are mirror image, this side and this side are mirror image, this currents and this currents will be same. Even after coming here, this third branch current, I don't know. Just concepts, sir. See, current will come, it will divide into 3. I cannot do current division because they are not parallel and not even path resistance in all paths are equal. But what I can argue at least, because with respect to this dotted axis, this side and this side are mirror image. So this current and this current will be equal. Then this third branch current, I don't know. But again, this side and this side will be equal. Due to which drop here and drop here is equal. So V1 equal to V2, that two nodes are at same potential. And here, because this current and this current are equal, these drops are equal, these drops are equal. So V3 equal to V4, V3 equal to V4. That is the big thing we can observe. Okay. However, V5 is not equal to V6. Yes, however, V5 is not equal to V6. Please understand. So, with respect to common axis, Yes, with respect to common axis, yes, please understand. V1 equal to V2 and V3 equal to V4. Yes, V1 equal to V2 and V3 equal to V4. Now I will join such nodes which are at same potential. Yes, I will join such nodes which are at same potential. So I'm joining 1 and 2. Yes, I'm joining 1 and 2. And then I'm joining 3 and 4. I'm joining 3 and 4. Now fold the network, sir. Yes, now joining this. Now fold the network. Fold network. Okay, fold the network along the common axis. Yes, fold the network along the common axis or mirror image axis. Now see, because I identified such nodes which are at same potential, that is V1 equal to V2 and V3 equal to V4. However, V5 is not equal to V6, please. Okay, because this is at higher potential, this is at lower potential. So now if I join, now listen. See, first of all, yeah, this is A and this is C that I'm not disturbing. And already adjacent to A5 is there, adjacent to C6 is there. This is sixth node, this is fifth node that I'm not disturbing because they are the axis nodes. Because they are the axis nodes. Okay, and this is 1 ohm, 1 ohm. But here what we joined such nodes which are at same potential. So we joined 1 and 2 and we joined 3 and 4. Okay, we joined 1 and 2 and we joined 3 and 4. Chalo. Now if you join 1 and 2, now this one become parallelism. Now this one after bending, na sir, see after bending this part to this part, you bend it from up to down, join 1 and 2. So this 1 become parallel half. Yes, 1 become parallel half. And even this 1 please understand, this 1 become parallel half. This is also half. Okay, and here also this 1 become parallel half. Yes, this 1 become parallel half. Yes, now left side also this 1 become parallel half. 1 become parallel half. Okay, this is also. And then if you see this 1 also become parallel half. 1 also become parallel half. Okay, now please understand what we did. Yes. Now if you observe, yes, now if you observe everybody, yes, now if you observe, now this is A and this is C. Okay, this is A and this is C. Now this 1 plus 2 I am writing here and 3 plus 4 I am writing here. Okay, now if you observe, A to 1 plus 2 is half, A to 1 plus 2 is half. Then C to 1 plus 2 is also half. Yes, C to 1 plus 2 is also half. Then A to 3 plus 4 directly. Now this becomes a simple node. 5 and 6 are simple nodes now. Directly A to 3 plus 4 is 1.5. 1 plus half is 1.5. That is 3 by 2. And C to 3 plus 4 is also 1.5. That is 3 by 2. And finally, 1 plus 2 to 3 by 4. 3 plus 4 is also half. Now this is perfectly a balanced pitch. Now this is perfectly a balanced pitch. Current cannot flow through half. Open it. So now finally RAC will be, after opening this 1 plus half plus half series 1 is in parallel to 3 by 2 plus 3 by 2 series 3. So it is 3 by 4 ohms. It is 3 by 4. Wonderful question. So in this problem, directly current division not possible because the path resistance in all paths are not equal. The path resistance in all paths are not equal. That is the first thing. So directly current division not possible. Then what I did, I applied two more techniques. One, yes, I want to identify such nodes which are at same potential and join them. But to identify which nodes are at same potential, for that first step is mirror image. So after getting the mirror image property, then yes, join step 2. This is step 2 where join nodes which are at same potential. Join nodes at same potential, which are at same voltage. That is the shortcut. That is note 1, note 2 I used now, sir. The tricks I used. See this trick and this trick I used. Okay, and I got these answers. Okay, that is wonderful. Now let us go to the B bit. Yes, let us go to the next bit like RAD. Now see, same network. Observe now what is RAD. Of course, all are 1 ohms. Yes, I'm not writing, but okay, it is understood all are 1 ohms. Okay, now RAD are the adjacent terminals, any two adjacent terminals. RAD are the adjacent terminals. Okay, any two adjacent. Even this become RAD, this become RAD, this become RAD, this become RAD, this become RAD. So RAD are any two adjacent terminals. Okay, now RAD has any two adjacent terminals. Now here also, if you try to implement Ohm's law, listen carefully. If you try to implement Ohm's law, the current division is not possible because first of all, no two elements are parallel, and moreover, the path resistance in all paths here again is not equal. Please understand. First of all, current division is applicable only if elements are parallel. No two elements are directly parallel, and moreover, path resistance between AD in all paths are not equal. The path resistance between AD in all paths are not equal. So again, what I will do, I will join such nodes which are at same potential. Directly, if you can look and do, that is fantastic, but it is not possible in a mirror image. So here also step 1. Yes, here also step 1, express as mirror image. Mirror image symmetry I want. Okay, chalo. Now again notes are, give any numbering. See, I need RAD. Okay, now give any numbering, it's up to you. Okay, let this be 1, let this be 2, let this be 3. Okay, let this be 4, let this be 5, let this be 6. Numbering is not important. How you are placing is important. Okay, now see here. A and D are in the same axis. Again, what I'm trying to do, everybody should observe this. Yes, A and D, I'll put on same axis. This is A and this is D. Okay, that I put on same axis. But this time you see now, directly between AD, there is a resistance 1 ohm. So this resistance 1 ohm I wrote here. Okay, then how I am placing the node, see 1 here, 2 here. Chalo, I will place 1 here, 2 here. Okay, then similarly 4 and 5 this side. 4 here, 5 here. Okay, okay, 4 here. Then 6 and 3, of course. Okay, 6 is opposite to A here. Okay, then opposite to D. 6 is opposite. 3 is opposite to A. Okay, 3 is opposite to A. Okay, 3 is opposite to A, and 6 is opposite to D. Okay, 6 is opposite to D. Chalo, this is what I did. Now let us see. Now A to 1 1, A to 2 1. Chalo, A to 1 1, A to 2 also 1. Okay, very good. Then here D to 5 1, D to 4 1. Okay, D to 5 1 and D to 4 1. Okay, this is also okay, done. Very good. Then 3 to 1 1, 3 to 2 1. Okay, 3 to 1 1 and 3 to 2 1. Okay, chalo, 3 to 1 1 and 3 to 2 also 1. Very good. Okay, then here also 6 to 3 1 and 6 to 5 1. Okay, 6 to 3 1 and 6 to 5 1. 6 to 3 and 6 to 5. Okay, 6 to 3. This let me write here. Okay, everybody, 6 to 3 also let me write first. 6 to 5 1 and 6 to 3 1. Okay, that you not forget. Okay, 6 to 3 1 and 6 to 5 1. 6 to 4 is also 1. Okay, 6 to 4 is also 1. And then finally 1 to 4 is 1. Okay, 1 to 4 is 1. Yes. Now, sir, you may say, sir, how to express? Now, if you write a virtual axis, yes, if you show this uncommon axis, that is from here to here, suppose you show an axis, yes, from here to here. Now, you may be confused with this 1 ohm. Yes, I know. And also 2 to 5. Let me correct it. Yes, 2 to 5 is there. Yes, 2 to 5. See, sir, everybody, even this see. Total 12 branches, I have to check it. Okay. 2 to 5 is also there. Yes, 2 to 5 also. Very good. Okay, now, so total 12 branches, you see now. 4, 4. Yes, 3 plus 1, 4. Chalo. Now, listen. Now I want resistance between, however, RAD or AD. Now you may say, sir, this 1 ohm at the bottom is confusing us. Now to prove our concept of mirror image, now see this 1 ohm I will write like 2 to parallel. Listen now, to argue like this, see this 1 ohm I am writing, everybody should watch the trick here. See this 1 ohm I will write like, yes, listen now, this 1 ohm I will write like 2 ohm, and this also I will make it like 2 ohm. Okay, 2 ohm in parallel, like that I will get. Now you see, now it is mirror image. That is a trick to explain our idea. See, actually, bottom 1 ohm is there, sir. Bottom 1 ohm was there. But I wrote that, but I wrote 1 ohm as 2 in parallel. 2 parallel is 1 only. Nah. Now you can say, yes. Now you can argue. Now you can argue. This side and this side are mirrors. This side and this side are mirror. Now you can identify which nodes are at same potential. So the nodes which are equal distance from this common axis are mirror image. So here node 1 and node 2, here also V1 equal to V2, and here also V3, V4 equal to V5 here. V4 equal to V5, please. Okay, na? V4 equal to V5. V4 equal to V5. Understood? Now joining them, sir. Now fold the network upside down along this axis. Now if you fold, yes, the shortcut is coming. Now this is, however, A. Yes, this is A and this is D. And already along the axis 1 is there, that you don't forget. Already along the axis 1 is there. Now by folding, top 2, bottom 2 become, yes, after folding top 2, this is the reason, sir. Identifying such nodes which are at same potential. Top 2, bottom 2 will become 1. Okay, na? Top 2, bottom 2 will, however, become 1. Will, however, become 1. Okay, na? Top 2, bottom 2 will, however, become 1 between 3 and 6. Okay, between third node and sixth node. Okay, they become 1 between third node and sixth. Okay, now I'm rewriting back. To express mirror image, first I wrote 2 parallel. Now I'm rewriting back. Then, sir, now joining, see, now joining such nodes. Yes, now joining such nodes which are at same potential. 1 and 2 I'm joining. Okay, and this 3 and 4, 4 and 5 I'm joining. 4 and 5. Okay, now see here. Because of this, what happened? First, 1 ohm I wrote, yes, this I wrote, and these 2 parallel also I wrote it. Okay, na? Then, what about remaining? Now see, between 1 and 2, these 2 parallel. Okay, 1 and 2 joined. Yes, 1 and 2 I will join together. Yes, what I'm doing here is, see this 1 and 2 I'm joining here. Okay, and this 4 and 5 also I'm joining. Okay, so because I joined 1 and 2, yes, what I can do now, 1 and 2 I join, these 2 become parallel. 3 to 1 and 2 is 1 parallel half. Yeah, 3 to 1 and 2 is 1 parallel half. Okay, and again, A to 1 and 2 is 1 parallel half. A to 1 and 2 is also 1 parallel half. Similarly, okay, now here also D2 4 5 is half. D2 4 5 is half. Very good. And here also 6 to 4 5 is half. 6 to 4 5 is also half. Very good. Then don't forget, see this branch 1 and 1 parallel. So directly between 1 and 2 and 4 and 5 is half. 1 and 2 and 4 and 5 is also half. This is also half. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and 11, 12. Everything 12 we got now, sir. 2, 4, 6, 8, 10, 11, 12. Chalo. Now I want resistance between A and D. Now, sir, it is very simple. Now see again if I rewrite like this. See, now it is very simple. Now this is A and D, my target. Okay. Now if you observe carefully, yes, this is something like this, where this junction is like 1, 2, and this junction is like 4, 5. 4, 5 nodes because we joined them. Here it is half. Now this is directly half. This is directly half. And again from 1 to 4, 5, all these become series. So half, 1, half. Total it is 2. Half, 1, half. Total it is 2. Okay. So yes, this is half, 1, and these 3 become series. So half, 1, half, 2. So now if you observe, yes, now if you observe, these 2 become parallel first. Okay, these 2 become parallel. 2 in parallel half. Okay, that is 1 by this into this by this plus this. That is, yeah, 2 and half, 5 by 2. So this becomes 2 by 5. 2 by 5. Okay, 2 by 5. Okay, first these 2 become parallel, that becomes 2 by 5. Now 2 by 5. Now if you take all these 3 in series, now if you take now if you take all these 3 in series, that means this part, and this part in series. Okay. Now this is half, 1 plus. This is 1 plus 2 by 5. There is nothing but 7 by 5. Now final answer. Finally. Yes, RAD is this 1 is in parallel to 7 by 5. That is this into this by this plus this. So answer is 7 by 12 ohm. 7 by 12 ohm is the final answer. See how interesting it is. Okay, take your time to learn, sir. Don't worry. In first attempt, no one in the world can learn. Even for me, do you think that I just got in 1 day or 1 minute? Think a lot, sir. Think a lot. Take your time. Don't worry. You're all my students and you are BTech completed or you are fresh or you are third year, second year. Take your time to learn. Okay, don't be in a hurry and nothing can be achieved in short times. Okay. See, here also current division was not possible because the path resistance in all paths are not equal. So I expressed first as mirror image. Then step two is, yes, step two I will repeat. Yes, step two is join nodes at same potential. Join nodes at same voltage. At same voltage. So which nodes were at same voltage? Looking at mirror image, this node 1, node 2, and node 3, node 4, node 5. So I joined them and simple series parallel, I got the answer. Answer is 7 by 12. Okay, na? So now, sir, the real big challenge. The real big challenge. First, IES objective. IES objective. What is RAB? Now let me see how many will do these things. A, B. Okay, these are A and B. All are R ohms. So only 1 minute I am giving everybody. Write some answer and keep quiet. Only 1 minute. Write some answer. RAB. Yes, 1 minute is over. Now listen. See here, there are many ways to do, but the shortcut, fastest. See, mirror image symmetry. See, directly if you observe between AB, directly if you observe between AB, they are mirror image. Yes, mirror image. But this is the center now. Don't disturb that. Now, with respect to axis, which nodes are at same distance? Yes, these two are at same distance, same potential. Join them. These two are at same distance. These two are at same distance, same potential. Join them. These two are at same distance, join them. So I'm folding again with respect to axis. If you fold along with the axis, this is A and this is B. This center node don't disturb. Okay, center node don't disturb. This RR parallel R by 2. This RR parallel R by 2. This RR parallel R by 2. Okay, and again this external RR parallel R by 2. This external RR parallel R by 2. And these two RR parallel R by 2. And these two RR parallel R by 2. Okay, so fold it. If you fold these two parallel R by 2, these two parallel R by 2, these two parallel R by 2, R by 2, R by 2. So now if you observe, this part is balanced pitch. This part is balanced pitch. When this part is balanced pitch and all are R by 2, center arm open, again R by 2, R by 2 series R by 2, R by 2 series R, again RR parallel R by 2. So finally, I will write here, finally, RAB is, now see, this is R by 2, this is R by 2, this is R by 2. 3R by 2 ohms. Very wonderful. So answer is 3R by 2. Now this is outstanding gate question. Gate ECE 2 marks. Gate ECE 2 marks. Wonderful. Find IRMS. RMS current through diode. Okay. This is wonderful question. One of the best questions in register reaction techniques. This is more challenging in fact. This is 10 sine t volt. This is 3 kilo ohm. 3 kilo ohm. Okay, I will use different colors to make you understand something very, very interesting. Okay, this is 3 kilo ohm, 3 kilo ohm, and this is 3 kilo ohm. Then this is 6 kilo ohm, 6 kilo ohm, 6 kilo ohm, 6 kilo ohm, 6 kilo, and 6 kilo. Then this is 9 kilo ohm, 9 kilo ohm, 9 kilo ohm. Okay, now I want RMS current through diode. Wonderful question. 2 minutes. Get 2 minutes. RMS current through diode. Yes, everybody listen now. See, here again, registers are not equal. Now you may be wondering, sir, here registers are not equal. How to do? Sir, here though registers are not equal, the path resistance in all paths are amazingly equal. See, now when diode is forward bias, see when supply is positive, diode is forward bias, it will conduct. Then this point, yes, this point one is at highest potential. This point, okay, is like lowest potential. Okay, I will put 0 and this I will put 3, sir, like our notation, like highest potential, like third floor. See, when the diode is forward biased in the positive half cycle, okay, when the diode is forward biased positive half cycle, this point is at highest potential 3 and this point is at lowest potential 0. Current always flow from high potential to low potential. But because this is 3K, 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 listen now, this pink color, 3K, 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 the drops will be equal and these points will be at same potential like second floor, second floor, second floor. I can join them when they are at same potential. Now from this point to here 2 6 kilos, here also 2 6 kilos, here also 2 6 kilo ohms. Again the drops will be equal. So this point will be like at first floor, first floor, first floor, but equal. So again I can join which are at same potential. That is the trick. So here though resistors are not equal. Now you see the path resistance from 3 to 0 and all paths are equal. Now you always travel from high potential to low potential. 369, 369. 369, 369, 369. So everywhere again path resistance. So here the trick is though resistors are not equal, but the path resistance in all paths are amazingly equal. So you can do current division and write KVL, or direct shortcut is join such nodes which are at same potential. I use the second trick which is faster. Now this is third, however this is third, okay, and this is 0. This is where our diode and source is connected. This is where our diode and source is connected. Okay, diode and source is connected. Okay, and the source is 10 sine t. Okay, 10 sine t. Okay, now then you see now this is like 2. Okay, this is like 1 because I joined such. Now listen, from 3 to 2, see, from 3 to 2, 3 kilo ohms are parallel. 3 kilo ohms parallel become how much? 1 kilo ohm only. Okay, then you see, yes, then you see from this 2 to 1 node, from this 2 to 1 node, 6 kilo ohms in yellow color are parallel. 6 kilo ohms in parallel again become 1 kilo, again become 1 kilo. And then finally, if you see from node 1 to node 0, yes, from node 1 to node 0, 9 kilo ohms are parallel. 9 kilo ohms are parallel is 3 kilo ohms. Yes, 3 kilo ohms. Now I need RMS current to diode. Now listen, see, without diode, it is normal that I is V by R total. That is 10 sine T by R total. Now total 3 kilo, 1 kilo, 1 kilo, 5 kilo. So I would have been how much without diode? Without diode, I would have been 2 milli sine T amperes. But with diode, now I'm writing here, but with diode, now listen, with diode, it becomes what, sir? With diode, it becomes a half wave rectifier because positive cycle it will conduct, negative cycle it will block. It becomes half wave rectifier, uncontrolled. Of course, this is uncontrolled. So half wave rectifier means if you see, yes, 0 to pi, 2 pi to 3 pi, like that. So 0 to pi, 2 pi to 3 pi, like this. So in half wave rectifiers are, yes, IRMS is IM by 2. This I will teach you in 5th chapter. Most of you know also. In half wave rectifier, if it is a full wave rectifier, IM by root 2. But if it is an half wave rectifier, IM by 2. So finally, this IRMS is IM by 2. What is IM? See, 2 milli is, because 2 milli sine T, that IM is 2 milli. 2 milli by 2, answer is 1 milliampere is the final answer. Final answer. Okay, is the final answer. Okay, wonderful question, sir. Wonderful question. Now I'm increasing the standard further. This is gate, electrical, 2 marks. Okay, find current I. Find current I. Okay, this is wonderful question again. Find current I. I need this current I. So do it again, 2 minutes. Wonderful question. 2 minutes. I need I. Yes, I need I. Yes, here also everybody, please understand. See, this is a non-planar network. Yes, this is a non-planar network. But sir, yes, but I will express mirror image and join such nodes which are at same potential C. With respect to voltage, I want current I is V by R. So where source is connected here now this becomes my target terminals. So now I will draw an axis here. Yes, if you draw axis, this side and this side are mirror image. Chalo, now with respect to axis, this point and this point are at same distance, so same potential join them. Now with respect to axis, this point and this point are at same distance, so same potential join. So I fold here, fold, okay, fold here horizontally, okay. Now if I fold here horizontally, see now, this 1 1 parallel become half, okay, 1 1. Here also bottom 1 1 parallel become half. But here this 2 becomes a self loop. See if I fold here, this 2 becomes a self loop, current cannot flow. Here also this 2 becomes a self loop. If you fold and join, see if you fold and join, If you fold and join, this 2 becomes a self loop, current cannot flow. Then finally, by joining this and this, sir, all this 1 1 become parallel half. Yes, 1 1 parallel become half. Okay, na? Yes, this 1 1 parallel become half. And also this 3 3 parallel become 3 by 2. 3 3 parallel become 3 by 2. Okay. So now, sir, because this 2 is self loop, this is self loop, current cannot flow because there is no potential difference. Current cannot flow. You can remove. So finally, this R total will be R total. See this half of 1 plus half in parallel to 3 by 2. Half in parallel to 3 by 2. So this is 1 plus, okay, 3 by 4 by 2. So this is 1 plus 3 by 8. That is 11 by 8 ohms. So R total is 11 by 8 ohms. I am writing neatly. Yes, it is 11 by 8 ohms. So finally, this I is 11 by R total. That is 11 by 11 by 8. It is 8 amperes. Wonderful question. It is 8 amperes. See, sir, the tricks help you to do in 1 minute. Okay. So take your time to learn fantastic questions. Now I'm going to another gate ECE question. If each branch is 1 ohm, then RAB is dash. If each branch is 1 ohm, RAB is dash. It is an infinite ladder in all direction. Or infinite grid, I will say. It is an infinite grid in all direction. Okay. Yes, it is an infinite grid in all direction. It's like a planar, two-dimensional infinite grid, like north, east, west, south. And each branch resistance is 1 ohm, and I want RAB. Okay, I'm giving you 2 minutes. Try something. I need RAB. Yes, everyone see. Now here we cannot apply ladder trick because in ladder at least the ladder was going in one direction, so that infinity plus and minus one infinity we can do. But here with respect to this AB, all four directions symmetrical pattern cannot be distinguished. Please understand. In ladder at least it is going in one side. Yes, I can take that infinity plus and minus one infinity by identifying a periodic segment. But here all four directions the periodic segment cannot be distinguished. Approximate answer some students are giving. No, sir, but engineering is about mathematical modeling and accuracy is rare. So that ladder trick failed. Okay, first that ladder trick failed. Okay, then mirror image symmetry I can write. Yes, with respect to AB, if I write an axis, see with respect to AB, if I draw an axis and show mirror image, I can join nodes which are at same potential, but later again it is useless. See, even you join such nodes, but rest of the network is again you cannot do anything. So that mirror image trick also will fail. Now, if you try to apply directly Ohm's law, now listen carefully again. If you try to apply Ohm's law directly between AB, so if you try to apply Ohm's law directly between AB, that is V by I ratio, but you cannot do current division again. You cannot do current division. The reason you cannot do current division because path resistance in all paths are not equal. See, A to B, this is one small path, this is bigger path. So even current division not possible. Even current division not possible. So what I want to argue is now this is beyond what we have learned. First of all, ladder in all four directions, identifying the periodic segments, distinguishing or separating network is not possible. Second, mirror image symmetry, joining nodes you can do, but that has no use after the first step. Third, directly try to apply Ohm's law, but current division is not possible as path resistance in all paths are not equal. Okay, all our ideas fail. Then what to do? Now here we apply, yes, here we apply superposition theorem, SPT. Wonderful concept. SPT. What is superposition theorem? Superposition theorem is additive property. Additive property. What is superposition theorem? It is additive property. What it will say? The effect produced in any element or network. See, the effect produced in any element or network when all sources act at a time. The effect produced in any element or network when all sources act at a time is also equal to sum of individual effects. Okay, directly between AB, I cannot do current division because path resistance in all paths are not equal. Neither they are symmetry nor they are, they may be symmetry, but current division not possible as path resistance in all paths are equal. And joining nodes virtually also will not help you after the first step. So because all the previous ideas failed, now I'm applying what? Superposition theorem. What is superposition theorem? Superposition theorem is additive property, where sum of individual effects is total effect. Now see the trick here. Chalo, see the trick everyone. Step 1. Now in step 1, what I'm doing everybody, to the same infinite grid. Watch this. To the same infinite grid. Okay, where I want resistance between AB. Now what I'm trying to do, watch carefully. See in the first step. Okay, because I need resistance between A and B now. So in the first step, I will inject current at A, but I will collect the current somewhere at infinite node away from A. Okay, yes, please understand. So, yes, in step 1, I'm inject current at A, but I will collect current at infinite node away from A. I will inject current at A, but I will collect current at infinite node away from A. Okay. Step 1, I will inject current at A, but I will collect current at infinite node away from A. Okay. Yes, I injected current at A, but I will collect current at infinite node away from A. Okay, I will inject current at A, but I will collect current at infinite node away from A. Now, because this current is collected at infinite node away from A, now I can say the path resistance from A to infinity in all paths are same. See, directly between AB is not correct, sir, because from AB, see, by looking at AB, see, this is one smaller path, this is bigger path, this is much bigger path. See, path resistance in all paths are not equal, but concept of this infinite node you see. So I'm injecting current at A and collecting at infinity. Now I can say the path resistance from A to infinity in all paths are equal because infinity plus 100 is infinity, infinity plus 1000 is infinity, infinity minus 20 is infinity, infinity plus 1 is infinity, infinity plus 5 is infinity, like that. Because I am collecting that current at infinite node away from A, now I can argue the path resistance from A to infinity. The path resistance from A to infinity in all paths are same. Yes, the path resistance from A to infinity in all paths are same. Okay, like I will give an example, sir. See, I stay at Hyderabad. Okay, I stay at Hyderabad. So anyone in this batch stay Kerala? Anyone raise your hand? Do you stay in Kerala? Anyone? Anyone? Yeah, some students raised. Very good. See, I stay at Hyderabad. Now listen, sir. Listen to the example. See, I stay at Hyderabad. You stay at Kerala, or some students in Maharashtra, Gujarat, etc. Now listen. See, I stay at Hyderabad. You stay in Kerala. There is a distance from Hyderabad to Kerala. There is a distance from Hyderabad to Kerala, but from both of our houses, Moon is at same distance, na? Yes or no? Everyone tell me. From Gujarat to Moon, from Hyderabad to Moon, from Kerala to Moon is almost same or not? Raise your hand. Yes or no? Yes or no? See, from Gujarat to Moon, from Kerala to Moon, from Pakistan to Moon, from America to Moon is same because Moon is a very, very long distance path. Moon is a very, very long distance destiny. So that is a shortcut, sir. See here, directly between AB, I can give voltage actually, but if you give voltage directly between AB and try to find the current division, it is not possible because path resistance in all paths are not equal. Neither it is parallel nor series, and nothing you can do. But what is the shortcut here? I'm injecting current at A but collecting at infinity. Now, because I'm collecting current at infinite node away from A, now I can argue the path resistance from A to infinity in all paths are same. Because infinity is such a long distance node, yes, away from A, that infinity plus and minus anything is infinity. Like, and there is a distance from Hyderabad to Kerala, like A to B. But I will argue the distance from Hyderabad to Moon is equal to Kerala to Moon because this infinite node is like a moon. Now I can argue the path resistance from A to infinity in all paths are same. Now because path resistance in all yes is all paths are same. Now I can do current division rule. So this I is coming. It will divide into 4 equal parts. This is I by 4, I by 4, I by 4, I by 4. But again after this coming here I by 4. Now from here, this node to infinity, again path resistance in all paths are equal. Again from this node, yes everybody, again from this node to infinity, the path resistance in all paths are equal. So this I by 4 further divides into 3 equal parts. I by 4 further divides into 3 equal parts. What are the 3 equal parts of I by 4? I by 4 by 3, I by 12, I by 12, I by 12. Okay na? So now, yes, I still want to do Ohm's law. Okay, now, but this is not the final answer. Why? Because I need resistance between A to B, not A to infinity. Na? So what I will do? Yes, I will take a segment voltage. I will take a segment voltage. Let this be VAB dash. VAB dash. Okay, because I want resistance between A and B finally. So this VAB dash will be this voltage plus this voltage. See, this voltage between A and B will be this voltage plus this voltage. What is this voltage? I by 4 into 1. Yes, what is this voltage? I by 12 into 1. I into our Ohm's law. So this is I by 3. That is step 1. Now see, step 2 is again interesting. Now to the same infinity grid where I want resistance between AB, where AB is the opposite diagonal corners of one of the internal mesh. Okay. Now I want, yes, I want resistance between A and B. Now this time what I will do is, yes, this time I will inject. Listen carefully. This time I am injecting current at infinite node away from B. Infinite node. This time I am injecting current I at infinite node away from B, but I will collect the entire current at B. Yes, this time I am injecting current I at infinite node away from B, and I am collecting current at B. This time I am collecting current at infinite node away from B, but I am collecting at B. This time I'm I'm injecting current at infinite node away from B, but I'm collecting at B. Infinite node away from B at collecting at B. Okay, collecting at B. Okay, na? So now again, can I argue the path resistance from B to infinity in all paths are same or not? The path resistance in B to infinity in all paths are same or not? Yes, the path resistance from B to infinity in all paths are same. So this time the current will converge uniformly. So this is converging here I by 4, I by 4, I by 4, and I by 4. Yes, again this point to be so infinity. This point to infinity, the path resistance in all paths are equal. So again this will converge equally from 3 sides. So I by 4 by 3, I by 12, I by 12, I by 12. But I want resistance from A to B, not B to infinity. Yes or no? I want resistance from A to B. So let this be another sub voltage VAB double dash. VAB double dash. Now what is this VAB double dash? This VAB double dash is equal to this voltage plus this voltage. What is this voltage? I by 12 into 1 plus this is again how much? I by 4 into 1. So this again become I by 3. This again become I by 3. Now, according to superposition theorem, sum of individual effects is total effect. That I am joining step 1 plus step 2. I am joining them, sir. Yes, I'm adding the effects. Now it is the same network, but I'm adding the effects. Please understand the concept here. It is network is same. I'm not joining two networks here. Network is one and the same. I'm joining the effects. This is A, this is B. Now see the effect now. In the first case, I injected current at A and collected it at infinity. In the first case, I injected current at A and collected at infinity. In the second case, I injected current at infinite node and collected at B. In the first case, I injected at A and collected at infinity. In the second case, I injected at infinity and collected at B. Now, this infinite node where I am collecting and this infinite node where I am giving are my same nodes. This infinite node where I am collecting and this infinite node where I am giving are my same nodes, where incoming current equal to outgoing current. Incoming current equal to outgoing current, yes, KCL satisfied. Incoming current equal to outgoing current, KCL satisfied. So, in the first case, I'm injecting current at A and collecting at infinity. In the second case, I'm injecting current at infinity and collecting at B. So at that infinite node, incoming current equal to outgoing current. Yes, if that infinite node incoming current equal to outgoing current, KCL satisfied. So final, it is as if that I'm giving at A, going to infinity, and giving at infinity and collecting at B is A to B. So this is finally giving at A. Yes, this is finally giving at A. Yes, giving at A and collecting at infinity at B. Because A to infinity and infinity to B is A to B. And at that infinite node, I'm collecting and I'm giving. KCL satisfied, law of conservation of charge is satisfied. So if I put that continuity superposition theorem, yes, if I put that superposition theorem, A to infinity is going and again from infinity it is coming back to B. Now this is my target because I want resistance between A, B now. Yes, but this total voltage now will be VAB now, total voltage VAB. But according to superposition theorem, these linear parameters like voltages can be added. So this VAB will be VAB dash plus VAB double dash. But what is VAB dash? Yes, I by 3 and this is also I by 3. So I by 3 plus I by 3. That is 2I by 3. So finally from Ohm's law, VAB is, R, I will write like this. Let me correct it. I want resistance now. Yes, RAB will be VAB by I. VAB by I. That is 2 by 3 ohms. 2 by 3 ohms. Wonderful concepts. So here I applied what? Superposition theorem. Okay, here I applied what? Superposition theorem. And the answer is 2 by 3. Okay, na? Wonderful problem. Okay, so please understand this. Very, very interesting. Okay, do it, sir. Take your time to learn. Okay, that is a wonderful problem here. Yes, now I'm going to another important model here. Yes, what is RAB? RAB. This is A and B. This is Vx. And this voltage is Vx by 2. There is a dependent source for the first time now. 1 ohm, 2 ohm, 3 ohm. Everyone copy this. I am going to explain now what is RAB. Okay, now listen. See, in this problem, there is a dependent source. See, unlike independent source, you cannot remove here. If that was independent voltage source, for passive property, voltage source is shorted, current source is open. But this is a dependent source now. Dependent source will have some internal sub-circuit resistance. So that we should include now. Now in this case, again reduction not possible. So apply Ohm's law. So when problem is only with dependent source, yes, I know this network is not working. I know because there is no independent source, or it is not working. But you should apply Ohm's law by making it working. Okay. So in such problems with pure dependent sources, we should include their internal sub-circuit resistance. Here we cannot do any reduction. So what we have to do? Apply Ohm's law. So now I am applying Ohm's law. See now. So you can give voltage, find current, or give current and find voltage. See, let me inject a current of 1 ampere. Because I want resistance between AB, let me inject a current of 1 ampere. And I will find voltage across it. So now according to Ohm's law, this RAB will be voltage Vx by current 1 ampere. Okay, yes, this RAB will be voltage Vx by current 1. Why voltage Vx? Because at terminals AB, the Vx itself is the dependent parameter. That itself is the voltage across 1. Na? Ohm's law is voltage by current. Na? See, everywhere. See, even in the previous problem, Ohm's law is voltage by current at the target terminals, VAB by I. So here also Vx by 1, because here I took 1 ampere. You may say, sir, why you took 1 ampere, sir? Why can't I take anything you can take, sir? Ohm's law is valid for homogeneity. You take 1 ampere, 2 ampere, 100 ampere, 1000 ampere, anything, answer will come same. Ratio will come same. Okay, na? So I took 1 ampere because easy calculation. So when you see problem with dependent source, already dependent parameter we don't know. So that is the reason I gave some numerical value here. Calculations become easy. Okay, so I injected 1 ampere and I will find the voltage across it. But what is the voltage across it? Vx given. So Vx by 1 ampere is resistance. Ohm's law. Chalo, now see. Because it is series, first of all, current is equal in all the elements. And that is current how much? 1 ampere. We are injecting already 1 ampere. So current is equal across all the elements. So now to find Vx, I will write a KVL. But when 1 is going through 1 ohm, this is 1 volt. When 1 is going through 2, this is 2 volt. When 1 is going to 3, this is 3 volt. 3 volt. Now happily I will write a KVL. So happily I will write a KVL. Okay, if you write a KVL, yes, if you write a KVL, this is minus Vx plus 1 plus 1. Okay, so plus 1 plus 2. Okay, minus Vx plus 1 plus 2. Okay, plus Vx by 2 plus 3 equal to 0. So Vx by 2 is 6. So Vx is 12 ohm. Now finally from Ohm's law, RAB is Vx by 1. That is 12 ohms. This is 12 volts, of course. This is 12 volts voltage, and this is 12 ohms. Okay, na? Everybody see again, I will explain. It is applying Ohm's law because dependent source alone cannot work. Okay, so because this problem is a pure dependent source, it is not working. We should include the internal resistance. So I apply Ohm's law. I injected current and I got voltage by KVL. Because current of 1 ampere is in series, so voltages are easy to find. So I wrote a KVL, I got the answer. Okay, now. Now, sir, I'm giving the gate bit. Wonderful gate bit. Yes. What is RXY? What is RXY? So this is a transistor BJT model. Most of you don't know. You will see such circuits in analog now. Yes, it's an application from analog. I need RXY. XY are these terminals. I need RXY. Everybody. See, everyone take a break also. Now it's almost 8:40. So 9:10 come back. Please take a break and keep trying. And after the break, we'll continue, sir. So I'm giving break for breakfast, and we'll join at 9:10. Yes, everybody. Are you there? Please raise your hand. Yes, everybody, please. Today I'm going a little sluggish, sir. Yesterday, video recording was done in AS Academy and I was really tired. It went up to night 11 o'clock. So really, I'm tired today, but still, chalo. Now listen, everyone. See, this problem is again problem with only dependent source. Actually, this network cannot work alone because there is no independent source. Okay, this network cannot work alone because there is no independent source. So how to find resistance by applying Ohm's law? Okay, how to find resistance by applying Ohm's law? Like give voltage, find current, or give current, find voltage. Okay, now give voltage, find current, or give current, find voltage. Now I will take voltage because it is a parallel nature network. Now listen here. Let me inject 1 volt. Let me inject 1 volt. I will find I total. So now Rxy according to Ohm's law is 1 volt by I total. Anything is okay, sir. See, in the previous model, I gave current and I asked voltage. In this model, I'm giving voltage and asking current. Anything you can do. Here also, you can give current and find voltage. It's up to you. But here, parallel nature, not giving voltage is easy and faster. So I give voltage of 1 volt. Now see here, I need I total. But to find I total, I will apply KCL at this junction. I will apply KCL at this junction. Okay, 4 currents because the degree of this node is 4. Chalo. When 1 volt is across, now listen carefully. When 1 volt is across, yes, when 1 volt is across 100, this is becoming how much? 1 by 100. Similarly, when 1 volt is across total 9 plus 1, 10K, when 1 volt is across 10K, this is 1 by 10K. Okay, when 1 volt is across 10K, this is 1 by 10K. Okay, 1 by 10K. So clearly you compare now, IB is minus 1 by 10K. When IB is minus 1 by 10K, this becomes minus 99 by 10K. When IB is minus 1 by 10K, this becomes minus 99 by 10K. Minus 99 by 10K up means minus 99 by 10K up means 99 by 10K down. Okay, minus 99 by 10K up means 99 by 10K down. Okay, yes, minus 99 by 10K up means 99 by 10K down. Okay, na? Chalo, now I can apply KCL. Now if you apply Kirchhoff current law, incoming currents to this node, I total is equal to outgoing 1 by 100 plus 1 by 10K plus 99 by 10K. This I total is 1 by 100 plus 1 by 10K plus 1 plus 99, another 100. So I total is 2 by 100, which is 1 by 50. Now finally Rxy is 1 by I total. That is 1 by 50. Answer is 50 ohms. Answer is 50. Wonderful question it is. Okay, na? And calculations are also equally important. Okay, answer is 1 by 1 by 50, 50 ohms. Okay, na? Now this is another unique question given in IES. What is the effective resistance? Effective resistance seen by the voltage source. Okay, what is the effective resistance seen by the voltage source? What is the effective resistance seen by the voltage source? So I'm giving 18 volts here, 3 ohm, 6 ohm, 9 ampere. What is the effective resistance seen by the voltage source? Okay, what is the effective resistance seen by the voltage source? Now here effective resistance is different, sir. See, what is effective resistance? Effective resistance is working resistance. See, effective resistance is equal to working resistance. Effective resistance is equal to working resistance. Please understand. Effective resistance is the resistance offered by the network to the source under working condition. Effective resistance is the resistance offered by the network to the source under working condition. Okay, effective resistance is working resistance. Okay, now it is not Thevenin's resistance. Thevenin's resistance is open circuit resistance, then open circuit voltage, current also open, 3 in parallel to 6 is 2, that is Thevenin's resistance. But I'm asking effective resistance. So effective resistance is working, sir, don't disturb anything. So as it is, without disturbing anything, I should apply Ohm's law. R effective is 18 volt by I total. Effective resistance is working resistance without disturbing network. Disturbing without disturbing the network. Okay, without disturbing the network. So it is 18 volt by I total. So, but what is this now? 18 by 3, this is 6 amperes. 18 by 6, this is 3 amperes, and this is 9 amperes. So total 9 plus 9, this is also 18. So I total is also 18. 18 by 18, it is 1 ohm. 1 ohm. If I ask Thevenin's resistance, that is different. That is 2 ohms, 6 in parallel to 3. But here effective resistance, there is a meaning, sir. Effective resistance is different. Now again IES question. What is effective resistance seen by voltage source? Voltage source. What is the effective resistance seen by the voltage source? What is the effective resistance seen by the voltage source? Shall everyone do it? What is the effective resistance seen by the voltage source? So here again apply Ohm's law, because working resistance we should not disturb anything. So this effective resistance is again simply V by I. Now see, now there is a current dependent current source. Out of I by 3 went. Here directly we cannot get answer because dependent source is there. So I will apply Ohm's law. See, out of I by 3 went. So this is automatically 2I by 3. Now 2I by 3 plus I by 3 is again I. So I'm writing a KVL like this. So if I write a KVL like this, yes, if I write a KVL like this, okay, that is minus V plus IR plus IR equal to 0. So V equal to 8I. So R effective is V by I, which is 8 ohms, which is 8 ohms. Okay, na? 8 ohms. Okay, that is 8 ohms. Okay, na? So with this, I covered all the resistor reduction techniques. Sir. Okay, na? Chalo, now I'm going to module 3 of chapter 1. Module 3, this is basic DC circuit analysis. Basic DC circuit analysis. Okay, now basic DC circuit analysis is all about fundamentals. Okay, na? KCL, KVL, Ohm's law, Kirchhoff law, fundamentals. So now my questions are very, very interesting and simple, but this practice is very, very essential for me. Okay, na? So this is the first question I'm giving. This is a graph of a network I am giving. Here, this is a graph of a network. Okay, this is 12 milliampere. Okay, this is 9 milliampere, and this is 10 milliampere. My question to you is, what is I1, what is I2, and what is I3? Okay, na? Similarly, second question I am giving. I'm giving second question. This is 10 amperes. This is 8 amperes. This is 2 amperes. This is 6 amperes. Okay, here again, what is IX, IY, IZ? Chalo, do it, everybody. Application of Kirchhoff current law. Application of Kirchhoff current law. Chalo, everybody. In the first bit, I need IX, sorry, I1, I2, I3. In the second bit, I need IX, IY, IZ. Kalyan, you are saying, Kalyan, raise your hand. Kalyan. Kalyan. Kalyan, why you write no? Only problems you do. Why you want to copy notes? We are sharing PDF with you, na? Take a rough paper and do problems when I give, not steps and copying everything. Okay? No, sir. It is not possible that I wait for every individual students here. Notes we are directly asked to share. So every day I am uploading the notes PDF copy. So that printout or soft copy will be there. Only take rough notes and paper pen and do along with me. Okay, don't come here to copy notes and by heart something. This subject is a practice subject, please. So this is directly KCL. Everybody listen now. Yes. Though these two are graph is a skeleton of a network. Now I'll apply KCL here. If I apply KCL, incoming current 12 milli is equal to outgoing current I1 plus 9 milli. So I1 is clearly plus 3 milliampere. So plus 3 ampere confirm that the given reference direction is practical direction. Now if you apply KCL here, again incoming 9 milli is equal to outgoing I2 plus 10 milli. So I2 is minus 1 milliampere. Minus 1 confirm that the actual current is going opposite to the reference. Minus 1 confirm that the actual current is going opposite to the reference. Now similarly, if I apply KCL here also, incoming, yes, 10 milli plus I3 is equal to outgoing 12. Okay, outgoing 12. So I3 is plus 2 milli plus 2 confirm that the given reference direction itself is a practical direction. So finally the answers are, see, I1 is 3 milliampere, I2 is minus 1 milliampere, and I3 is plus 2 milliampere. Plus answer confirm that the given reference direction is practical direction, but minus answer confirm that the actual direction is opposite to reference. Okay, now here, let me also apply KCL here. Everybody, see, don't directly apply here or here because there are two unknown parameters. First, I will apply here. If I first apply here, incoming current 6 is equal to outgoing IZ plus 10. So IZ is minus 4. Minus 4 confirm that the actual current is going opposite to the reference. Now I'll apply here also. Incoming IY plus 8 is equal to outgoing 6. So IY is minus 2 ampere. Minus 2 again confirm that the actual current is going opposite to reference. Now I can happily apply. Actually, now I can happily apply. Yes, now I can happily apply KCL here. Incoming. Yes, what is incoming? 2 plus Ix is equal to outgoing 8. So Ix is 4 ampere. Ix is 4 ampere. 4 ampere confirm that the given reference direction is the practical direction. 4 ampere confirm that the given reference direction is practical direction. Okay. Given reference direction is practical direction. Okay. Okay, now let me check. If I am correct, let me check here. If you check here, all incoming 10 is equal to outgoing is also 10 because 10 is coming here. 4 plus 2 is also 10. So KCL satisfied. So our answers are IZ is minus 4, IY is minus 2, and IX is plus 4. Plus answer confirm that the given reference direction is practical direction. Minus answer confirm that the actual direction is opposite to, yes, opposite to reference. Okay, actual direction is opposite to reference. Okay, now I'm giving next set of questions. Yes. Ten volts, 5 volts, 20 volts, 50 volts, V1, V2, V3. Chalo, what is V1, V2, V3? What is V1, V2, V3? Okay. Then here I am giving another question. Here, what is V1 and what is V2? This is 10 volts. This is R1, but this is R2. And this is 18 volts and this is 12 volts. Now my question is, what is V1 and what is V2? Chalo, answer these two. It is implementation of KVL. Chalo, answer these two, everybody. Yes, applying KVL. Everybody see apply KVL. See if I write the first KVL here, minus 10 clockwise plus 5 plus 20 plus V1 is 0. That implies V1 is how much? Yes, it is minus 15 volt. What does minus 15 indicate? Yes, minus 15 indicate the actual voltage polarity is ulta to the reference. So this is now minus plus. This is now minus plus 15. That is the meaning, sir. That is the meaning. So minus 15 indicate the actual voltage polarity is ulta to the reference polarity. For current directions, for voltages polarity. Minus current means opposite direction, minus voltage means opposite polarity. Okay, now again if I write a KVL clockwise, yes, plus 50 minus V2 minus 20 equal to 0. Okay, plus 50 minus V2 minus 20 0. So V2 is plus 30. Now this time plus 30 confirm. Yes, this time plus 30 confirm. Yes, the actual polarity is same as practical. Okay, now I am writing the third KVL. Yes, if I write third KVL, minus V1. Yes, it is minus V1. Okay, okay, I will substitute directly. Now because I know these two, now let me substitute. Chalo. Plus 15, because I know this, plus 15 plus 30 plus V3 is 0. So V3 is minus 45. Again, minus 45 confirm that the actual voltage polarity is ulta to the reference. So V1 is minus 15, V2 is plus 30, V3 is minus 45. Plus answer means given reference polarity is practical, minus answer means actual voltage polarity is opposite to reference. Okay, na? That is the meaning here. There is a meaning about polarity for voltage and direction for current. Okay, polarity for voltage and direction for current. That you have to remember. Okay, polarity for voltage and direction for current. Okay, so now I'm going to the right side problem. Now here also I need V1, V2. Okay, here also I need V1, V2. But sir, common sense. If this is the voltage across R1, this also is V1 across R1. Why? Because both are series. If both are series, first of all, current is same. If both are series, first of all, current is same. Current is same, resistance is same, voltage should be same. See, if this is V1, this also should be V1, sir. If this is V1, this also should be V1. Why? Because resistors are equal. In series, current is also equal. So voltage must be equal. And why I took this polarity? Because in this element, if this is given positive, in this given element, it is positive. Current is entering positive now. That means current is going right side here. If here also, if current goes right side, as per the given polarity, this should also be plus the left side. Because in a passive element, the direction in which current enters is taken as positive. Now with these basics, happily I will write a KVL here and a KVL here. So if you write a KVL, just starting from here, minus 10 plus 2V1, V1 plus V1, 2V1 plus 12 minus 18 is 0. So that implies V1 is, okay, see 2V1 is 28 minus 12, 16. V1 is plus 8 volt, plus 8 volt. Then second KVL if I write, plus 18 minus 12 plus V2 is 0. So V2 is minus 6 volt, minus 6. V2 is minus 6. Okay, so the answers are V1 is plus 8, V2 is minus 6. V2 is plus 8, V1 is plus 8, V2 is minus 6. Okay. Okay, that is the answer. So here V1 is minus 8, V1 is plus 8, V2 is minus 6. Okay. So I'm giving another IES question here. What is Vx? Six ohms and this is 5 ohms. Okay, now my question is, what is this voltage Vx? What is this voltage Vx? Now another question in IES objective, find V1 minus V2. Okay, find V1 minus V2. Ten volts 1 ohm, 20 volts 2 ohm, 30 volts 3 ohm, 40 volts 4 ohm. So what is V1 minus V2? So what is V1 minus? So do it everybody. Okay, I'm going with solution C. I need voltage Vx. Vx is the open circuit voltage across the target terminals. Okay, now Vx is the open circuit voltage across the target terminals. There is no element here. But to find Vx, I need to write a KVL. But to write a KVL, first I should know the voltage across passive elements. So first I will do mesh analysis. Mesh is a closed path current. So if I do mesh analysis, it is minus 5 plus 6i plus 10 plus 5i plus 50 is equal to 0. So 11i is equal to minus 55. So I is minus 5. So minus 5 confirm that the actual current is going anti-clock 5. See, what I want to argue is minus 5 confirm that. Yes, minus 5 confirm answer that actual current is going, mesh current is going anti-clock 5. Now when actual current is going anti-clock 5, okay, this current also branch current is 5 anti-clock. This is also branch current 5 anti-clock. So it is 5 5 is 25. It is 5 6 are 30. 5 6 are 30. Okay. Now I'm writing a KVL here. And now I'm writing a KVL here. You can write any directions or clock, anti-clock, it's up to you. It's up to you. Okay. So if you write a KVL in the left side, minus 5 minus 30 plus 10 plus Vx is 0. So Vx is plus 25 volt. Plus 25 volt. Or you write even right side, minus Vx minus 25 plus 50 is 0. That also gives Vx as plus 25. Vx as plus 25 volts. Okay, Vx as plus 25. So both are independently correct. Okay, both are independently correct. Okay, now yes. Now find V1 minus V2. Find V1 minus V2. Okay, find V1 minus V2. Okay, please understand this. Find V1 minus V2. Now again to write V1 minus V2, I need to write a KVL. Okay, I need to write KVL. But to write KVL first, I need the voltage across passive elements, na sir. See, because he is asking to find V1 minus V2, see, I will take like this. Okay, I will take V1 minus V2 now, so I will take this as positive. Okay, I will take this as positive. Okay, this as negative, because it is now difference of V1 minus V2. Yes, so this difference I want, but I took this as minus and this as plus. Okay, na? So please understand. Now I need this V1 minus V2. I am just showing arrows to show, yes, that V1 minus V2 is the potential difference between these 2 points. Na? Okay, I will show this as X. Better I will show this as X. That X is nothing but V1 minus V2. Yes or no? Potential difference X is not the difference between 2 points. That is V1 minus V2 only. Now to get that, I will write a KVL. But to write KVL first, I will again do mesh analysis. Chalo. Again, I am doing mesh analysis. Okay, if I write a KVL, okay, mesh analysis. Yes, that mesh equation. Okay, starting from here, minus 20 plus 2, 3, 4, 1, 10i. All resistance together 10 in series. Minus 30 plus 40 minus 10 equal to 0. From that, 10i equal to, yeah, 10i equal to 20, I equal to 2 amps. I equal to 2 amps. Now once I is 2, yes, real current is 2. That means actual current going in this mesh, which is also the closed path current is 2. Which is also the closed path current is 2. Okay, now when 2 is going through 3, okay, 2 3s are 6 volts, 2 4s are 8 volts, 2 1s are 2 volt, and 2 2s are 4 volt. So now happily I will write a KVL here or KVL here. So that KVL will give starting from here, minus 20 plus 4 minus 20 minus 30. Okay, this is now minus 30. Okay, plus 6 plus X equal to 0. Okay, na? See, minus 20 plus 4. Okay, na? And this is minus, okay, minus 20 plus 4 minus 30 plus 6 plus X equal to 0. So X is equal to how much? Yeah, this is 50 minus 10, 40 volts. But X is nothing but V1 minus V2. V1 minus V2 is 40 volts. V1 minus V2 is 40. Okay, now V1 minus V2 is 40 volts. Okay, that is the answer. Okay, so now I am giving another interesting question. Everybody, these are very important DC basics, sir. Now in the next question, answer carefully, everyone. This is 66 milliamperes. Okay, so how much I'm taking? This is 66 milliampere. This is 10 kilo ohm resistance. This is 1 kilo ohm, 2 kilo ohm, 3 kilo ohm. And I need current I. I need current I. Similarly, okay, here I'm giving 120 volt, 2 kilo ohm, 3 kilo ohm, okay, 6 kilo ohm, 3 kilo ohm, 2 kilo ohm. Okay, this is 2 kilo ohm. Here I need voltage V. Okay, here I need voltage V. In the first case, I need current I. In the second case, I need voltage V. Okay, in the first case, I need current I. In the second case, I need voltage V. Now these are simple current division and voltage division rules, please. Okay, everybody. These are simple current division and voltage division rules. Okay, na? Yes, simple current division and voltage division rules. Now see, I know there is a 10 kilo ohms in series to 66 milli. Even then, the current until here will be 66 milli only. Why? Because current source in series to any element is redundant. Okay, now current source in series to any element is redundant and current is always constant. Now this 66 milli will divide into three branches, not current division. In three branches, we know now current division in three branches. This current I will be total current 66 milli into first product of remaining two. What is the product of remaining two? 1K into 3K, 3 mega by sum of products. 1K into 2K, 2 mega plus 2K into 6, 3K, 6 mega plus 3K into 1K, 3 mega. Now you remove this mega. So this is 11, 6 milli into 3, 18 milliamperes. 18 milliamperes. Okay, na? 18 milliamperes. Similarly, now I need this voltage V. Sir, we can apply voltage division if the elements are series. First, I will lump these three elements in parallel into single element. 6K in parallel to 3K, 2K, 2K, 2K parallel, 1K. Now, after lumping this into single element by they are parallel, why they are parallel? Yes, because they are parallel. After lumping this into single element, now I can do voltage division between these three series. Because these three parallel I lumped into single 1 kilo. Now this 2K, 1K and 3K are series. So voltage division rule. This voltage is total voltage into same 1K by some 6K. So this is 20 volts. This is 20 volts. We use 20 volts. Okay, we use 20 volts. Okay, na answer. We use 20 volts. Okay. Then here I am going to a question. Find V and find I. So in the previous problem, I did simple current division and voltage division, sir. But current division is possible if they are parallel. Yes, three elements in parallel. Voltage division is possible if they are in series. First I lumped this, then they become series. Okay. So now I am asking what is V and what is I. This is 10 volt. Ohm. 1 ohm. Okay, here another 5 ohms is there. 5 ohms is there. And here also another 3 ohms is there. Okay, now we observe everybody. Okay, now I need this voltage V and current I. Okay, now I need voltage V and current I. And I'm giving another question here. Okay, what is here also what is V and what is I? Next question also. Thirty amperes. And my question is, what is this current I and what is this voltage V? Okay, what is this? Now this I will write neatly. This current is 30 amperes. So what is V and what is I? హలో మామయ్య, అదే ఎప్పుడే తెలిసింది, అమ్మ చెప్తుంది. నేను ఇక్కడ బయటకు వస్తే అమ్మ చెప్పింది. అదే మీ బెస్ట్ ఫ్రెండ్ ఇక్కడ ఉండే కదా మన అంకుల్, స్టెంట్ వేసినట్టు కదా మామయ్య, స్టెంట్ వేస్తే చనిపోయారట కదా. Yes, now what is V, what is I? I need open circuit voltage and short circuit current. Now listen everybody. See what is the only resistance seen by this? See the only resistance seen by this is 5 ohms only. Why? Because short circuit in parallel to passive this won't work, and open circuit in series to passive also this won't work. So total resistance seen by 10 is only 5. So what is the current delivered then? 10 by 5 2. So automatically I is 2 amperes. I is 2 amperes. But when 2 amperes is going through 2, this is 4 volts now. This is 4 volts. So automatically V is also 4 volts. V is also 4 volts. Okay. So I confirm. Yes, I confirm. The answers are V is equal to 4 volts. Okay na? And I is equal to 2 amperes. I is equal to 2 amperes. Now right side problem is conductance. Everybody please listen. Right side problem is conductance. Ulta to resistance. Okay. Conductance is ulta to resistance. Okay. But be careful, sir. This is ladder network. So directly I know 30 amperes is series to 5 Siemens. 30 amperes in series to 5 Siemens. Even then this is 30 amperes. Yes, current source in series to anything is current constant. At this junction it will divide into two parts. At this junction it will divide into two parts. I can apply current division. Okay. But current division is applicable only if the elements are parallel. But these two are not parallel. It's a ladder. So first what I will do, I will lump the resistance here into single element. Yes, I will lump the resistance into single element, and that element and this element become parallel. Directly don't say this 4 and 4 are parallel, please. It is a ladder. First I will lump the segment of network until here into single element, and that element and this element becomes parallel. First of all, 3 and 6 series 2 parallel 4, 4 series 2 Siemens. Chalo, this is 2 Siemens, this is 4 Siemens. Now current division rule. This current is total current into same by sum. Same is 2, sum is 6. Same is 2, sum is 6. So answer is 10 amperes. Answer is 10 amperes. Okay, answer is 10 amperes. Okay, now out of 30, 10 went. So here it will be automatically 20. See, out of 30, 10 went. Why this? In conductance, it is proportional to conductivity. See, first I lumped, sir. 3, 6 series. Series conductance is ulta parallel to resistor now 2. 2 to parallel 4. 4, 4 series 2. That means this segment is 2 Siemens and this segment is 4 Siemens. Current division rule. This current is total current into same 2 by sum 6. 10 amperes. So out of 10, see now KCL, out of 30, 10 went. Out of 30, 10 went. So this has to be 20. Now, what is V in conductance? V is I by G. I by G. I is 20 by G is 4. This is 5 volts. This is 5 volts. So the final answers are V is 5 volts and I is 10 amperes. Okay, V is 5 volts, I is 10 amperes. Now here also the question is what is V and what is I? Okay, here also what is V and what is I? Now this is 8 ohms, 4 ohms, 6 ohms, 1 ohm, 2 ohm, and here what is V and what is I? But he gave a hint. The hint is this is 1 ampere. The current in 2 ohms is 1 ampere. That is a hint given. Okay, the hint given is the current in 2 ohms. Yes, the current in 2 ohms is 1 ampere. That is a hint given. And from that I need V and I. From that I need V and I. Okay, and also there is a gate 1 mark, easy bit. If V naught is okay 4 volts, then R is how much? Okay, if V naught is 4 volts, R is how much? Okay, if V naught is 4 volts, what is R? If V naught is 4 volts, what is R? Okay, do this, do immediately, everyone. Yes, do this. Yeah, basics of Ohm's law and KVL, sir. Kirchhoff's laws. See now, he gave hint, sir. He gave a hint. I need V and I, but with the given hint, if current is flowing 1 ampere through 2, this is automatically 2 volt, na? Passive notation. If this is 2 volt, this is also 2 volt because both are parallel. These both are parallel. Now 2 by 1, this is also 2 amperes. Now apply KCL. This is 2, this is 1, total 3 amperes. Now when 3 is going through 4, 3 fours are 12 and 3 6 are 18. See, sir, with the given hint, all the voltages I got. See, sir, with the given hint 1, 1 2s are 2, 2 volts because both are parallel. 2 by 1, this is also 2 amperes. Now this is 2, this is 1 KCL, this is 3, 3 4s are 12, 3 6 are 18. Now happily I can write a KVL. So if you write a KVL here, minus V plus 12 plus 18 plus 2 equal to 0. So V is, okay, plus 32 volt. Now once we got V is plus 32, 32 by 8, this is 4 amperes. 32 by 8, this is 4 amperes. Okay. Yes, 32 by 8, this is 4 amperes. Okay, 32 by 8, this is 4 amperes. Now if you apply KCL, now if you apply KCL, okay, this is 3, this is 4. So I is 7 amperes. So V is 32 volts and I is 7 amperes. V is 32 volts and I is 7 amperes. Okay, now? Now see the right problem. If V0 is 4, R is how much? Now see, if V0 is 4 volts, automatically this is also 4 volts because both are parallel. Out of 20, now see, out of 20, this parallel branches share 4 volts. Out of 24 volts means this has to be 16 volts. KVL, na? Out of 24 volts drop means remaining 16 should come here. Then automatically, this 16 by 16, this is 1 ampere. Okay. Now, this is 4 by 3, 2 by 3 ampere. Now, out of 1, 2 by 3, so this has to be 1 by 3 ampere. Now Ohm's law if I apply, R is V by I, V by I, V by I. So V is how much? 4, I is 1 by 3. So R is 12 ohms. R is 12 ohms. Okay. So R is 12 ohms. We'll stop here today. Okay, we'll stop here today, but we'll continue more aggressively tomorrow. Any doubts, please? Doubts, Pallavi? Pallavi doubt? Pallavi Ram take. Pallavi, any doubt? Tomorrow again 7 o'clock we'll go more aggressive, sir. Tomorrow. Actually today I told us yesterday video went up to 11. By the time I came it is 1 o'clock. I was fully tired, but okay, chalo, I'm doing some bit today at important problems. Anyone doubt? Okay, Pallavi. Okay, next Pranjali.
Hello, sir.
Tell me.
In the first question of today, that homework question, sir, why V5 node is not equal to V6? Sir,
Because,
that mirror image symmetry.
Listen. I understood. Listen. See, it is on the same axis. Yes or no?
Yes, sir.
Now left side node is subjected. Suppose you give voltage between A and C. Left side node is subjected to higher voltage and right side node is subjected to lower potential. Na?
Okay.
There.
Yes.
But the up and down mirror image, that is equal because you look upside and you look downside. That resistances are equal.
Yes.
So with respect to mirror image, the nodes which are at same distance are equal, but not in the mirror image. The nodes which are on the same axis cannot be at same potential. Na?
Yes, sir.
Understood? Huh?
Yes, sir. Thank you, sir.
Okay. Ashish.
Hello, sir. Sir, about the class, sir, tomorrow's class, sir. It is showing from 7 to 11.
What happened tomorrow?
Tomorrow's class, sir, it is showing from 7 to 11, 4 hours class.
Which class?
This one, network only, sir.
You want 7 to 11, huh?
No, sir, it is showing on the portal.
I'll find out. What you want? You want only from 7 to 10, huh?
No, sir. If syllabus ends as soon as possible, that will be good for us, sir.
See, actually, I am engaged in so many batches, including offline and video. Yeah, that is a problem. Being a network, initially what happened before Corona and all this came now, initially we started all the batches networks first. Then once that lockdown etc. came, then what happened? All networks over they considered and remaining subjects they completed directly. Now suddenly once the lockdown is lifted, now suddenly networks only is remaining for so many.
Sir, I joined late, sir. Means network control is also left. and so many subjects are left, sir. That's why. Means he once check, sir, because it is showing for till 11, 7 to 11. That's how I was asking to you.
No, it's okay. But what? No. What you want actually? You want up to as much as you can. You are telling.
Yes, sir.
Maybe after 25, I will after 25th or 26th, I will plan on 7 to 1 o'clock also. Give me some time because see now I will tell you my schedule also. See first your batch up to 10:30. Now from 12 to 4 I have to do studio work, that is Deeploan app. We are doing recorded videos, and then evening 6 to 8:30 also another offline class. So 3 classes are going on for me parallel. You understood? Hello? Yeah, Ashish, I am unable to listen to you. You are understanding? Ashish? Ashish? Ashish, your voice is not coming. Ashish, your voice is not coming. Okay, Gautam?
Sir, could you please tell that transistor problem, sir? I did not get it.
That resistance, equivalent resistance only, na?
Yes, sir.
Transistor is a dependent, transistor is a current dependent current source. Actually, such equivalent circuits you will get in analog EDC, where transistor model it is actually. Now, what is your doubt there?
This I did not understand, sir.
See, I want the resistance in between XY, but because this dependent source internal resistance also exists, we cannot do any reduction here. So I applied Ohm's law. Say like same previous problem. Here also only dependent source is there, na?
Yes, sir.
So here what I did, I gave voltage, I got current. That ratio of voltage applied at XY and current leaving at XY will give the ratio of resistance. So I introduced 1 volt, but to find I total, I applied KCL here. But to apply KCL first, I got the remaining branch currents. How? See, when 1 volt is applied across 100, this is 1 by 100, na?
Yes, sir.
Similarly, when 1 volt is applied across 10K, similarly when 1 volt is applied 10K, this is 1 by 10K, na?
Yes, sir. Yes, sir.
This source is driving current in the down direction because this is positive, this is negative. But IB is given opposite to practical direction of my reference, na?
Yes, sir.
So IB is minus 1 by 10K. If IB is minus 1 by 10K, this is minus 99 by 10K.
900,
Minus
yes,
99 by 10K means 99 by 10K down.
yes, sir. Understood, sir. Thank you, sir.
Now I applied KCL, I got I total and then R.
Yes, sir.
Okay. And here also, yes, RAB. Here also RAB. Okay. Now Soundarya, please talk.
Hello, sir.
Soundarya, tell me.
Yesterday problem, sir.
Tell me, what is your doubt? Tell me.
These points are non-linear component.
Non-linear component. Tell me, what is your doubt?
VI characteristics, once explain, sir, how to getting RD greater than RS.
See, first of all, if you take V equal to I square, you know this plot I plotted first. Green line you understood how I plotted, like I0, V0, I1, V1, I2, V4, I3, V9, like that it will come like this. Yes or no? Like parabolic.
Yes, sir.
Now, at any point you state, suppose, see, if the curve is like this, any point you take first static resistance, and that you take a tangent here.
Yes, sir.
From there you vary now anything. Now dynamic is change in voltage by change in current. So this slope is pakka greater than static, na?
Yes, sir.
Suppose you take any point. Suppose take this point or this point. Suppose first point you take this ratio as static. From there you confirm dynamic, it is more. Suppose even you take this point as static. From there you confirm it is dynamic is again more. So that means because of the curvy nature, which is parabolic, where homogeneity or proportionality is not valid here. Dynamic resistance is practically greater than static resistance. Na?
Yes, sir. Yes, sir.
Then remaining is all calculations only.
Okay, sir.
Then what I did, that to get the ratio of voltage by change in voltage by change in current, the given equation I differentiated. Then the dV by dt, di by dt is nothing but change in voltage by change in current. That itself is dynamic resistance, which is 2I. But from the same equation, V by I is I. But what is V by I at an instant? V by I at an instant is static resistance only, na?
Yes, sir.
So that I substituted here. So that
Okay.
so finally dynamic resistance is 2 times static.
Okay, sir.
Okay, na?
Okay, sir. Thank you.
Okay. Ashish.
Hello, sir.
Tell me, Ashish.
Yes, sir. That one when you resolve that symmetry question, sir, that cube question.
Tell me.
Sir, in that means once again we can fold that. No, sir. That when you solve by symmetry, sir, AC.
Tell me.
Yes, sir. You have folded along AC, sir.
Along AC.
After folding, can we fold once again, sir? That means you can see,
No,
sir.
It's about the target. See, the question will decide where to fold and how to fold. Target itself is AC, na. Now,
yes.
if you fold again, A and C will join. No use, na.
Okay, sir. Means for every point we have to again we have to redraw this.
If necessary, we can do again folding, but the target itself is decided there, na.
Yes, sir. Actually, I was trying that for AC only, and I was trying to get AD, sir. That's why that was wrong. Okay.
Yeah, AD also. This is the same way, right?
Okay, sir. Okay, sir.
Okay, right. Okay, everybody. Tomorrow 7 o'clock, I will go more aggressively. One student requested.
Yes,
Sir, why
sir.
can't- Tell me who is this? Pranjali.
Yes, sir. Yesterday's question, sir, we did that infinite ladder problems. Sir, in that we did that array in terms of RB question.
Yeah, tell me.
Sir, in that we substituted in place of RB, in that RB ladder, we put RA. But sir, if
Yeah,
we
understood. Suppose
RB,
you are, yeah. If you put RB in place of RA, then RA is 2 plus RB is also correct, but that option is not given. See,
okay,
if
sir.
you can put RB also in place of RA, then that becomes 2 plus RB is RA, na?
Yes, sir.
That option is not there. Correct. That option is not there.
Okay.
Okay?
Okay, sir. Thank you, sir. Yes, sir.
Right. So everybody tomorrow 7 o'clock.